heart within the mediastinum. This is not a human. This is some quadruped, maybe a cat or a rabbit. But we can see the heart. It's outside of the pericardium. The pericardial sac has been removed. You can see these little flaps right over here. This little flap is called the auricle. And within this auricle, we find the atrium. Right? Remember we drew kind of a little square representation of the heart? Remember that representation we did? The reality is, if we to draw it accurately, the atria are only a small fraction. And left versus right sides, the left side is so much larger. So if we drew it proportionally, it'd be more like so. The left side of the heart is larger, because remember, this is the pump to the systemic circuit for your nose and your toes and everything in between. The right side is a pump to the pulmonary circuit, so it's not really going that far, not much muscle mass. And the atria, think of atria simply as entryways. We'll talk about the atria functionally in a little bit, and we'll see that if you have AFib, atrial fibrillations, they're not doing their job, they're quivering, if you will, they can't contract, you can say, excuse me, I think I need to ride to the hospital. Whereas if you're having ventricular fibrillations, if your ventricles are quivering, especially your left ventricle, then that's as serious as a heart attack. That is deadly, right? So the completely different scenario. So we'll see the role of the atria is a little less significant than the ventricles, but nevertheless important. So on this illustration, the atria are actually included within this region here. This is the auricle, this little ear-like flap, and within that we find the atrium. And then back here is the left atrium. And so the atria are kind of insignificant compared to the ventricles. These are the ventricles. Also, the heart sits with the apex skewed forward a little bit, right? It's kind of tilted forward, not straight down, up and down, and then rotated to the left. So what you see on this heart is actually majority of the mass right along here. All of this is actually the right ventricle. Smaller than the left ventricle, but this is the right ventricle. Left ventricle is over here, rotated around that way to the left. And so anterior-most chamber of the heart actually ends up being the right ventricle, the smaller of the two ventricles. The left is kind of skewed to the left a little bit. Right? So stand anatomical position. So as an impact to the heart, and there is any kind of bruising on the pericardium, it's actually going to affect the right ventricle before the left ventricle, more likely to affect the right ventricle. Up here is the superior mediastinum, it would be right just deep to the sternum. And so you can see all the great vessels coming in and out of the heart, actually come in and out through the base of the heart. Nothing comes in and out the apex. Here are the two lungs. And since the left side of the lung or the heart is larger, the left lung is actually smaller. Your left lung has two lobes, and your right lung has three lobes. The main bronchi, the airway coming into each lobes, to each lung, the right side has a greater diameter than the left side. So statistically, you're actually more likely to get lung cancer on the right side than the left side of your body. Right? Why? Because the right lung is larger, processes more air, has a larger airway, if you will, than the left side, because the left side has this portion missing here that's actually referred to as the cardiac notch of the left lung, because that's the space for the left ventricle of the heart to occupy, right? Because the heart is larger on the left because that pumps the systemic circuit. Talk about structure function, right? All right, let's take a look at a little bit more of the histology of the heart. Now, we've talked about skeletal muscle, and so I want to show you the cardiac muscle, striated muscle. So right off the bat, we have a lot of ground covered. We know A bands, I bands, dark bands, light bands, right? We know that there are Z discs. We know that there are sarcomeres. But also here, unlike skeletal muscle, we have individual cells. These are not fused like skeletal muscle fibers, but these are individual myocardiocytes. These cardiac muscle cells are myocardiocytes. I think the name is self-explanatory. Myo meaning muscle, cardio meaning heart, and cyte meaning cell, right? So these myocardiocytes are connected by a series of structures. You can see them right here. These are called intercalated discs. These are really important. Within these intercalated discs, we're going to see a series of structures holding the cells together, desmosomes and adherence junctions and all kinds of goodies associated with cell structure, but also gap junctions. And these are going to be crucial for the conduction within the heart, for the function we see in just a minute. All right. So once again, intercalated discs And within the intercalated discs, we have gap junctions. Remember, this whole structure is not a gap junction. This is an intercalated disc. It contains gap junctions. And what gap junctions do is allow calcium to flow from cell to cell. So imagine this scenario. Imagine we have, let's just go with one cell here fires spontaneously, depolarizes, right? Remember what that meant for us? An action potential occurs. And this cell floods with calcium. Calcium enters the cell. In this case, it's going to come from outside of the cell. Calcium floods the cell, and all of a sudden the cell depolarizes, contracts, and now the concentration of calcium is millions of times greater inside the cell than outside, and greater than the neighboring cell. So through those gap junctions, calcium ions will flow which way? To every neighboring cell. Notice this kind of intercalated arrangement of cells. Every cell is in contact with several other cells through these intercalated discs. And as calcium flows into the neighboring cell, it carries a positive charge with it. And guess what happens? That causes the neighboring cell to depolarize. Calcium floods in. And that causes what? Then the calcium to flow to the neighboring cell. And so we have this wave of calcium spreading across the myocardium as it flows from cell to cell to cell, as each cell depolarizes, contracts, and then triggers a neighboring cell to contract. So all we need in the heart, really, unlike we saw with skeletal muscle, where we have to have specific innervations to muscle fibers by neurons forming motor units, here we need to have just one cell fire. One cell to spontaneously depolarize, and the result is we get a flow of calcium from cell to cell to cell. And so keep that notion in mind. We'll come back to that when we talk about the conduction pathway in the heart. We have to talk about that in just a little bit. We're not ready for that yet. First, let's talk about the gross pattern of contraction, what actually contracts, and then we'll talk about the synchronization. All right? While we're here, though, check this picture out. This is pretty cool. This is simple compound-like microscope. But this is actually of a heart, a hypertrophied heart, where a heart is enlarged because of overuse, if you will. It's like any muscle, it's going to grow, you have hypertrophy. But that's the bad thing in the heart. That means the heart is working harder than it has to. Something's impeding function, blood pressure issues, and so the heart has to work harder than normal to keep up with the demands of the body. So unlike exercise, this is actually an exaggerated function. But here you can see the individual myocardiocytes, striated muscle, right? Involuntary but striated, so quick contractions, and we see dark bands, light bands, dark bands, light bands, really clear. And you can see the intercalated discs. That's why I like the hypertrophied heart slides, because they really highlight those intercalated discs. So if you look carefully, there's one, there's one, there's one. So be familiar with those, what they look like under slide. Okay. All right. So let's take a look at. We'll come back to this histology, but let's take a look at the gross anatomy of the heart. And here we have a choice of how to do things. All right. I like learning things as a series of events. So if we look at the heart, and we'll go straight inside to look at the chambers. We'll look at the superficial view in just a moment. But I like to consider things as a series of events, or a series of structures involved in an event. And so for the rest of the semester, that's really going to be pertinent. That is the way you think about the rest of this class. That's the key. What I just told you is probably the most important things you're going to hear from me as far as how to study for this course for the rest of the semester. Pay attention to the series of structures involved in a process, no matter what system we talk about. Starting with the heart, we can talk about the flow of blood through the heart to and from the two circuits, the systemic and the pulmonary circuits. The left side is going to receive blood from the pulmonary circuit and pump it out to the systemic circuit. There's the aorta coming out. The right side is going to receive blood. So here is the blood is going to come in, and then it's going to go out the aorta, right? Then the right side is going to receive blood from either above the heart or below the heart from the vena cava, like we talked about. That blood will then enter the ventricles, and then from there, blood will pass into enter the atria, From there, blood will enter the right ventricle and then be pumped out. There's a pulmonary trunk going out to the left, and the right pulmonary arteries going to the lungs, right? The start of the systemic circuit. So it's everything we just talked about, but a prettier picture. So let's consider the path of blood. But the way I'd like to think about it is we have two choices. We can think about it as both sides simultaneously, which is really how it works. Both blood comes into both atria contract, both atria relax, Both ventricles contract, both ventricles relax. It's both sides almost simultaneously, fraction of a nanosecond separation between the two, and we'll discuss that in the atria just a little bit. In physio, we'll cover that in more detail. But to make things simple, let's first start off by learning just one side. We'll stick to the right side. We could just as easily start on the left. It's arbitrary, but let's start on the right side. And what we'll do is we'll leave a little bit of space, and then we'll fill in just what's different on the left side. A couple names will be changed, and that's all there's to it. So let's trace the path of blood through the heart, but we'll focus on the right side. All right? We'll do the Miss Frizzle example. You guys remember Miss Frizzle, Magic School Bus, how they shrunk the school bus and traveled through the body? Well, I'll be Miss Frizzle. All right? If we were in lecture, I would wear my Miss Frizzle outfit. No, I don't have one of those, fortunately. Fortunately for you and me. But I will, let's pretend we're traveling through the body, and now we're tracing, maybe riding an old red blood cell or a Magic School Bus, and we're going to come back to the heart by the superior and inferior vena cava into the right atrium, and we'll pick up our story there. And here's the trick. Remember the pattern. Atria contract, atria relax, ventricles contract, ventricles relax. It's going to be it's all going to be synchronized to those events. So let's start with everything's relaxed. The last contraction cycle. Let's pick it up from there. All right, so let's take a look at the heart. There's a little smaller picture just for reference, and we'll start making a list right here. So remember, we're only focusing on one side, but this is occurring in both sides. So we'll use the black pen, and blood will come into and this is going to be schematic. Blood comes into the right atrium. From which vessels? From above the hearts, from the superior vena cava and the inferior vena cava. So we can say the vena cavae, plural. But you know at this point the distinction between the two. One vena cava, AE is plural in Latin, right? So these are the vena cavae, both of them. So in this illustration, blood comes in from above and blood comes in from below. Yeah? Blood will then enter the right atrium, and here's the trick. It's kind of like coming into a classroom. Most students come into the classroom, they walk right into the class. So most of the blood, this is really important, something like 80% of that fluid will flow right through the atrium into the ventricle. Nothing's contracted, nothing has happened. So 80% is going to go into the right, remember we're sticking to one side, ventricle. You notice how I left a little line here for a reason. I'm going to fill that in a little bit. So 80% passes into the right ventricle passively. Right, so the fluid comes in and just flows on in through this opening. We'll describe that in just a moment. Without any kind of intervention, the force that brought the blood into the atrium continues on its way into the ventricle. So 80% of what the ventricle is going to eject eventually, it's called the ejection fraction. You'll get that in physiology. We're not going to really make a big deal of that concept here, but 80% of that final ejection fraction, what's eventually going to leave the ventricle, gets there passively. Nobody contracted, no one forces it in. But now we have to prime the pump. Now, remember, the first step is going to be the atria contracts. So in this case, we'll just stick to the right side. The right atrium contracts. What do I mean by that? The myocardium contracts. And please, please, please keep in mind, just speaking of the right atrium by itself is not accurate. Both sides are doing this, but we're just sticking to one side to make the story simpler. So the right atrium contracts, and that drives the remaining 20% of the final ejection fraction into the ventricle. Does that make sense? Pumps the rest of the blood into the ventricle. It primes the pump, if you will. It tops off the pump. So the ventricle atrium is not really pumping the blood, it's just pumping the blood. It's helping fill the ventricle. All right, here's an important thing. Atrium contracts, what happens to happen? What has to happen next? Right, so the right atrium contracts and 20% of the blood enters the right ventricle, right? Now, what's the next thing that has to happen? Atrium contracts, here's the key. Remember the pattern? Atrium relaxes. The right atrium relaxes, all right? So, atrium contracts, atrium relaxes, and only then do the ventricles contract. And this time we're sticking to the right side, remember once again. So the right ventricle contracts, and this is what we set everything up to. This is kind of our underlying thread. Right? This is the central event: contraction, relaxation of the ventricles. So as the right ventricle contracts, several things are going to happen. First and foremost, looking at the right ventricle, right, we can see that there are a series of one-way valves, either leading from the atrium to the ventricle or from the ventricle to the subsequent artery, in this case, the pulmonary trunk. These valves are simply, and this is really important, remember we made a big deal of that endocardium, right? The epithelium supported by dense irregular connective tissue. And so these valves are simply extensions of that endocardium, forming a series of flaps. Think of like a tent flap. Not a solid structure, right? Not a rigid structure, but of loose, solid, but yet solid structure, like a tent flap. And so sitting in between the right atrium and the right ventricle is the right atrioventricular valve. Sitting in between the ventricle and the pulmonary trunk, these little half-moon shaped valves make this the semilunar valve, or in this case this would be the pulmonary semilunar valve, because this is going to the pulmonary circuit. So as the ventricle begins to contract, remember from the previous state of contraction, these semilunar valves are closed and this atrioventricular valve is open. That's how the blood entered from the atrium to the ventricle. And as the ventricle starts to contract, this flap will shut closed. So that right atrioventricular valve sometimes usually abbreviated AV, right, will close. Now this valve has three little cusps on it, three little flaps, and so it's also referred to as the tricuspid valve. The right AV valve is also known as the tricuspid valve. So the right AV or tricuspid valve closes. And at this point, there's a couple of things we have to consider. First, so as the pressure starts to build inside this ventricle, as the walls start to collapse, if you will, as the ventricle starts to contract, imagine what's happening to the space. We have an enclosed space. This valve is closed, right? The semilunar valve is closed because of the back pressure of blood in the artery. We'll discuss that in a minute. That's keeping this valve closed. As long as the pressure in the artery is greater than the pressure in the ventricle, this valve will remain closed. But this atrioventricular valve, the tricuspid valve on this side, is going to readily start to close. And it starts to flip up. It will occlude this opening, but the problem is this is just like a tent flap. It's not a rigid structure. No, think more a tent flap rather than a door. And it'll swing back in the opposite direction. It could prolapse. So to prevent that prolapse, the atrioventricular valve, extensions of the collagen from the atrioventricular valve extend and form a series of ligaments called the chordae tendineae. The chordae tendineae are attached to a series of folds of the myocardium. Remember our term for fold was papilla. So these are referred to as the papillary muscles. There are a series of papillary muscles attached to the chordae tendineae on either side of the atrioventricular valves, right? Attached to the atrioventricular valves. So as the myocardium starts to contract, these papillary muscle are just extensions of the wall of the heart, of the myocardium. And so this myocardium, or the papillary muscle, contracts and pulls on these chordae tendineae, and it keeps them from swinging too far in the opposite direction, right? It makes them stop and close off the semilunar valve, right? So these are the papillary muscles, which put tension on the chordae tendineae, which prevent the atrioventricular valve from prolapsing. Let's spell all that out real quickly before we move on. So we have the papillary muscle. As this is occurring, the papillary muscle will put tension on the chordae tendineae, and you may have heard of some use the expression heartstrings, and that's what they're referring to. They actually look like little strings inside the heart. It's actually really cool. Inside the ventricles of the heart. Chordae tendineae, right? Tendineae. And as they do so, this prevents, right, so papillary muscles pull in the chordae tendineae, and this prevents the AV valve from prolapsing. right? Going back the wrong direction. And what would happen if it prolapsed? Well, then blood would flow backwards, and that prevents backflow of blood, right? We want blood moving in one direction. So this prevents blood from backing up, and that's a whole other set of dire consequences we can describe later. So back to our process here, our series of events. So as the right ventricle contracts, the AV valve closes, and the chordae tendineae papillary muscle keep it from prolapsing, right, swinging back the other way. And now what do we have? We have an enclosed space. The AV valve is closed, the semilunar valve is closed, and the pressure continues to build. In physiology, you'll talk about it as an isovolemic contraction, because iso meaning same and volemic meaning volume. The volume doesn't change of the ventricle, but the pressure keeps building. It's like a closed balloon, and you keep squeezing it. Eventually, the pressure in the ventricle becomes greater than the pressure in the artery. By the way, I'm never going to ask you about those pressures or those relationships for anatomy course. This is more part for physiology. But so you understand the big picture. As the ventricle contracts, the pressure eventually forces these AV valves, the pressure eventually forces these semilunar valves open, right? So right ventricle contracts, right atrioventricular valve closes. Oh, by the way, really quickly, as it closes, imagine a flat surface of a drum and fluid striking the surface of the drum. And you may have heard of this before, but you get a thump sound, right? If you listen to someone's heart, you hear a lub-dub, lub-dub, lub-dub. Those are called the heart sounds. And I don't like the terms lub-dub. If we're in Russia, we might call them lubsky-dubsky, right? So let's go instead with the first and second heart sound. And so that lub sound, that first heart sound, is caused by blood striking that closed atrioventricular valve, right? So as the ventricle contracts, we close the AV valve and we get that first heart sound, the lub, if you will. I'll put it in quotes, but please refer to it as the first heart sound in my class, okay? AV valve closes. We get first heart sound. Remember, it's not just it's striking, it's actually referred to something called the sound of Kortkopf. That turbulence that's produced is actually what creates that noise. And then eventually, as the pressure then builds, then this semilunar valve opens, right? So 3 events. 1, AV valve closes. 2, we get the heart sound. And 3, all because of the right ventricle contracting. And 3, we get opening of the, now look at this valve. It's leading semilunar, little half moons, leading to the pulmonary circuit, to the pulmonary arteries. So this is called the pulmonary semilunar valve. In physiology, it'll simply be referred to as a pulmonary valve because that's the only one, but this describes the anatomy of it and lumps it together with the aortic semilunar valve, which will describe it a little bit. So anatomy, where we categorize all these things, we use the full term, pulmonary semilunar valve, but pulmonary valve means the same thing. All right, and then blood is going to leave the ventricle, enter the artery, and so blood enters the artery, right? Which artery? The pulmonary artery, or the pulmonary trunk. That was the ventricle contracting. Atria contract, atria relax. Ventricles contract, what has to happen next? The ventricles must relax, right? That's our only logical conclusion here. The right ventricle relaxes. As the ventricle relaxes, what happens next? Think about it. We have these semilunar valves. All of a sudden, the pressure in this artery is greater than the pressure in the ventricle, and the blood goes, hey, I want to go back, right? It's forced backwards. But these semilunar valves catch the blood, and they slam shut. Think almost like little parachutes. They slam shut. So as the right ventricle relaxes, the opposite of what happened up here occurs. 1, the semilunar valves are going to close. And let's use the correct term here, the pulmonary, because we're only speaking of one side. Closes, right? Pulmonary semilunar valve closes. As it closes, we get the second heart sound, right? Closing the valves, sound of Kortkopf, and we get the second heart sound, also known as Dubsky, right? Or dub. of lub-dub fame, right? So lub-dub, so the second heart sound, right? So the first heart sound is caused by what? Closing of the AV valve. Second heart sound closing of these semilunar valves. And so far we're only speaking of one side. And then, now that there's no pressure in the ventricles, guess who opens up again? This is the tricuspid valve, right? The right AV valve opens. And where are we? Right back where we started. Blood starts to fill the atrium, flowing straight through to the ventricle. And look at that penmanship deteriorate. Isn't that amazing how this goes? All right. What you guys don't realize, I've been pausing this and I had time to go to the grocery store, wearing my mask, of course, and keeping away from all the other miscreants, and dealt with a temper tantrum, helped my daughter assemble some furniture, took a meeting with a lawyer, and all this while my penmanship quickly deteriorated. So there's an excuse. All right. The joys of recording lectures in your garage. Alrighty. So far so good? Alright. Now this is one cycle. Alright, so think about this. Listen to the noise. I'm just tapping both my hands on the desk, right? Or my workbench, that is, my assembly table. And every time I'm using both my left and right hand, you guys can't see it, but lub-dub, 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 right? Left and right side are striking at the same time. But the reality is, one of those cycles, lub-dub, that's what we just described here, right? The entire cycle is just one, the entire list is just one cycle of contraction. And remember, this is happening at the same time on the left side and the right side. So on the left side, we have the same architecture, just slightly different names. So it's really easy just to first learn it on one side and then just remember the difference on the other side. So on the left side, the left atrium receives blood from the pulmonary veins. Right? Left and right pulmonary veins. 80% passes passively into the left ventricle, right? Then the left atrium contracts. The remaining 20% enters the left ventricle. The left atrium relaxes, and finally the left ventricle contracts. As the left ventricle contracts, the left atrioventricular valve only has two flaps, so it has actually two names. It's called the bicuspid. Put it over here. Bicuspid, because of its two flaps, or it has this pointy shape that's referred to as a mitral shape. So a mitral valve is the same thing as the bicuspid valve, is the same thing as the left atrioventricular valve. So that's like a good test question to you guys. So two more names for the left AV valve are bicuspid and mitral. All right. Once that happens, we get the first heart sound, same thing, and then the instead of pulmonary semilunar valve opening, this is going to the aorta, so this is the aortic semilunar valve opens, blood enters the artery. In this case, it's going to be which artery? Back here on the right side, that was the pulmonary trunk. On the left side, that's going to be the aorta. Start of the systemic circuit. Yeah? Then last but not least, let's finish strong. The left ventricle is going to relax. The aortic semilunar valve is going to close. We get the second heart sound, and then the left atrioventricular valve, also known as the bicuspid or mitral, opens up again. And remember, this is happening at the same time on both sides. So once you're comfortable with this, I would go back and run through it with an illustration, right? Blood enters both atria, flows passively into both ventricles. Both atria contract, prime the pumps, if you will, right? Both atria relax, and then both ventricles contract. As the ventricles contract, the two AV valves close, creating the first heart sound. Blood then opens, then the semilunar valves open, and blood enters the corresponding arteries. As the ventricles relax, blood closes the two semilunar valves, and we get the second heart sound, and the atrioventricular valves open, and we're right back where we started. All right, so that's one cardiac cycle. So the next thing to consider is going to be, how do we regulate all of this? How does this occur in a coordinated manner? The left side and right side are doing this at the exact same time, nearly the exact same time, right? That's going to have to do with those gap junctions and those intercalated discs and that flow of calcium, and the dense irregular connective tissue of the endocardium. So make sure you're comfortable with those ideas before we get to the next lesson and this flow. This is the mother of all ideas here.